A Chinese solar manufacturer has now pushed a full-size Perovskite-on-silicon tandem cell beyond 32% efficiency and built a 776-watt module around the same next-generation technology. The company is Tongwei, and the more important number may actually be 5 megawatts. That is the capacity of the automated pilot line Tongwei is using to figure out how to manufacture these cells repeatedly, not just make one perfect sample in a laboratory. As of August 2026, Tongwei says its commercial-size 210 by 105 mm tandem cell has reached 32.68% efficiency, while its 21066 format module has reached 776 watts. This is not mass production yet, but it is a serious attempt to give ordinary crystalline silicon a second light-absorbing layer and push solar panels onto a new efficiency curve. There is an important correction to make right away. A 776-watt panel is not, by itself, a world record for panel power. Tongwei has already demonstrated conventional heterojunction modules above 800 watts, and other giant utility panels can also reach very high wattages simply because they are physically large. Wattage without panel area can be misleading. What makes this 776-watt result unusual is what is inside the panel. Instead of relying on one silicon junction to absorb the sun, Tongwei stacks a thin perovskite solar cell on top of a silicon heterojunction cell. Two absorbers, tuned for different parts of sunlight, work together. Solar panel wattage is measured under standardized laboratory conditions: 1,000 watts of light per square meter, a cell temperature of 25 degrees Celsius, and a defined solar spectrum. That gives manufacturers a common yardstick, but it is not the same thing as what a panel produces on a hot roof at 3 in the afternoon. A larger panel intercepts more sunlight, so it can post a bigger watt number without being more efficient. Efficiency is the cleaner measure of how effectively the panel uses its area. This matters with 21066 utility modules because they are enormous compared with common residential panels. Tongwei's established 21066 format measures about 2.384 meters by 1.303 meters, roughly 7.8 feet by 4.3 feet. At that scale, adding even 1 percentage point of module efficiency can mean dozens of extra watts without enlarging the frame, which is exactly why the industry keeps chasing better cells rather than simply making panels wider. That addresses a basic problem silicon engineers have been wrestling with for decades. Silicon is an excellent solar material. It is abundant, well understood, durable, and supported by an enormous global manufacturing base. But every semiconductor has an energy range it handles best. Sunlight contains photons with many different energies. Some are too weak for silicon to use. Others carry more energy than silicon needs, and the extra energy is mostly lost as heat. Even an ideal single-junction crystalline silicon cell eventually runs into a physical ceiling. Fraunhofer ISE puts that practical theoretical limit at about 29.4%. Modern commercial silicon cells are already getting uncomfortable close to that wall. Top-end back contact and heterojunction devices can reach the high 20s at the cell level, while very good commercial modules now sit in the mid-20s. Engineers can keep improving contacts, passivation, optical coatings, metal fingers, wafer quality, and manufacturing precision. Those improvements still matter, but the closer silicon gets to its single-junction limit, the harder each additional fraction of a percentage point becomes. Perovskite changes the problem instead of merely polishing the old solution. A perovskite is not one specific chemical. It describes a family of materials that share a particular crystal structure, and their composition can be adjusted so they absorb different parts of the solar spectrum. In a tandem cell, the perovskite layer is tuned to catch higher energy light, including much of the blue and green portion. Lower energy red and near-infrared light passes through to the silicon cell underneath. The two layers divide the work more efficiently than either could alone. Fraunhofer calculates that adding a perovskite top cell, only about 500 nanometers thick, can raise the theoretical efficiency ceiling of a silicon-based tandem to roughly 43.3%. 500 nanometers is half of 1 micron. A human hair is tens of microns thick, so the potentially transformative part of this device is not another heavy slab of material. It is an extremely thin active layer deposited onto an already advanced silicon cell. Tongwei is using silicon heterojunction, usually shortened to HJT, as the bottom cell. HJT starts with a crystalline silicon wafer, generally N-type silicon, then uses extremely thin layers of amorphous silicon to passivate the surfaces. Passivation is basically defect control. At the atomic level, a bare silicon surface contains places where electrical charge can recombine and disappear before it reaches the circuit. The thin amorphous layers reduce those losses. Transparent conductive oxide layers then help collect current while still allowing light through. HJT is especially attractive for tandem development because much of its processing happens at relatively low temperatures. Perovskite materials can be sensitive to heat, so a manufacturing sequence that avoids very hot steps is useful. Tongwei has spent years developing HJT cells, copper interconnection, thinner wafers, and ways to reduce expensive silver. That means the Tandem project is not starting from an unfamiliar silicon platform. The company is trying to bolt a new photovoltaic engine onto a production technology it already understands. The difficult part is making the perovskite layer behave on a real industrial silicon surface. Commercial silicon cells are not flat under a microscope. They are textured with microscopic pyramids. Those tiny structures reduce reflection and help trap light, which is good for silicon efficiency, but they create a nightmare for coding. Imagine trying to paint an even film over a field of microscopic sharp hills and valleys while keeping the film chemically uniform to within tiny tolerances. Thin spots, uncovered areas, poor crystal growth, or composition changes can all create electrical losses. That is where Tongwei's two-step deposition process matters. The company describes its route as vapor deposition, followed by a solution step. In simplified terms, part of the perovskite precursor is first deposited by evaporation. A second chemical treatment then reacts with that framework to form the finished perovskite absorber. Tongwei says it has developed control over nucleation and crystallization on fully textured silicon, allowing the coating to conform to the pyramids instead of forming an uneven blanket across them. This work did not appear overnight. In 2025, Tongwei researchers published a study on wide bandgap perovskites grown directly on commercial textured HJT silicon. Their two-terminal tandem device reached a certified 31.4% efficiency. The top perovskite had a bandgap of 1.73 electron volts, and the bottom silicon wafer was only 110 microns thick. The group used a carefully controlled sequential annealing process at roughly 100 to 150 degrees Celsius, with treatment times under half an hour. Those are temperatures and times that industrial equipment can realistically handle. Two-terminal is important. In this architecture, the perovskite and silicon subcells are electrically connected inside one device and present a single pair of external contacts. That makes the finished cell look more like a conventional product from the outside, but it creates another engineering constraint. The current generated by the two subcells needs to be closely matched. If one layer produces less current, it can hold back the other. Designers therefore have to tune thickness, bandgap, optical transmission, and interfaces as a complete system. By September 2025, Tongwei had commissioned what it described as the industry's first fully automated megawatt-scale Perovskite-Silicon tandem pilot line. The line is rated at 5 megawatts and covers the path from cell fabrication toward module integration. A 5 megawatt line is tiny compared with today's giant silicon factories, which are measured in gigawatts. 1 gigawatt is 1,000 megawatts. But a pilot line has a different job. It exposes problems that never show up when a researcher hand builds a few square centimeters at a time. A factory needs repeatability. Every large wafer has to receive nearly the same film. Coating speed has to be predictable. Chemistry has to remain stable. Equipment has to stay clean. Defects have to be detected before bad cells travel farther down the line. Yield matters because a process that makes spectacular cells half the time and scrap the other half is not competitive. Throughput matters because an extra 20 minutes per wafer can become a major bottleneck when production scales into millions of cells. Tongwei's newest numbers suggest the company is improving on that manufacturing side. The firm says the monthly average efficiency on its pilot line is now above 28%. That figure deserves as much attention as the 32.68% champion commercial-size cell. A record device proves what the process can do at its best. An average tells you something about how often the process works. Tongwei has not published enough public production data to treat this as proof of gigawatt-ready manufacturing, but it is exactly the kind of metric the industry has to improve before tandem cells become ordinary products. The 776-watt module needs similar context. Tongwei calls it a 21066 format, a large utility-scale form factor built around 210mm class cells. Panels in this family are roughly 8 feet long and more than 4 feet wide. That means they are intended primarily for large ground-mounted solar projects and big commercial installations, not a small suburban roof where one person casually carries a panel up a ladder. And again, the wattage is not the whole story. Tongwei's conventional HJT technology has already produced a 2,384 by 1,303 mm module above 802 watts at 25.83% module efficiency. So why care about a 776 watt tandem? Because the tandem cells are still early in their manufacturing learning curve. Silicon HJT has had years of optimization, while the perovskite layer introduces new optical, electrical, chemical, and packaging problems. The significance is that Tongwei is now building large tandem modules in an industrial format instead of reporting only postage stamp laboratory cells. There is also a gap between the efficiency of the best tandem cells and the finished module. A module adds glass, encapsulant, spacing, interconnections, edges, bus bars or conductive structures, and other inactive area. Every one of those elements can introduce optical or electrical loss. A 32% cell does not automatically produce a 32% panel. Closing that cell-to-module gap is another major engineering task, and it becomes harder with a new material that dislikes heat, moisture, ultraviolet exposure, and mechanical stress. Reliability is probably the biggest unanswered question. Silicon modules are expected to sit outside for decades. They bake in summer, freeze in winter, absorb ultraviolet light, experience humidity, wind, hail, mechanical loading, and thousands of daily temperature cycles. A utility developer financing a solar farm does not mainly care whether one new cell reaches an impressive efficiency in a test lab. The developer cares how much electricity the module will produce over 20 or 30 years. Perovskites have historically struggled here. Heat, moisture, oxygen, ultraviolet radiation, electrical bias, and ion movement inside the material can degrade performance. Wide bandgap perovskites used in tandem cells can also suffer composition changes under illumination. Researchers have made substantial progress, but durability is still the reason serious manufacturers use words like pilot line, validation, and demonstration instead of pretending the transition is finished. Tongwei says it is attacking that problem with a dual ultraviolet protection system, combining a light conversion functional layer with a blocking layer. It has also developed low-stress encapsulation and ultra-low temperature interconnection processes. That matters because normal module lamination and soldering conditions can place thermal and mechanical stress on a delicate tandem stack. The company is also building outdoor validation programs, so cells and modules can be measured under real sunlight rather than only accelerated indoor tests. Other companies show that the reliability race is becoming more concrete. Qcells announced in July 2026 that its Perovskite-Silicon tandem modules had received TÜV Rheinland certification against IEC and UL qualification and safety standards. Those tests include punishing cycles of heat, cold, humidity, mechanical stress, and other conditions designed to expose weaknesses. Passing them does not guarantee a 30-year lifetime, but it is a much more meaningful step toward bankable hardware than an efficiency record alone. Oxford PV has gone farther commercially in another direction. It shipped Perovskite-on-Silicon tandem modules to a customer in the United States back in 2024 and has been producing pilot products in Germany. Its current modules are around 25% efficiency, and the company has said it wants to reach mass production in 2027 while extending product lifetime. Meanwhile, a US company called Tandem PV opened a 40-megawatt demonstration factory in California in 2026. So China is not alone in pursuing this technology. China is, however, moving on several fronts at once. LONGi holds the current certified world record for a 2-terminal crystalline silicon perovskite tandem cell at 35.5%, verified by the European Solar Test Installation. LONGi has also announced a 100-megawatt tandem pilot line. Tongwei is emphasizing compatibility with HJT manufacturing. Trina Solar has discussed gigawatt-scale tandem capacity later in the decade. The competition is shifting from proving tandem physics to proving tandem manufacturing. That distinction matters because solar history is full of brilliant technologies that could not beat silicon on cost, lifetime, scale, or financing. Silicon's strongest advantage is not simply efficiency. It is the gigantic industrial ecosystem behind it. Wafers, glass, frames, junction boxes, encapsulants, inverters, mounting systems, factories, standards, installers, banks, and insurers already understand silicon modules. Any replacement technology has to fight all of that. Perovskite-Silicon Tandem takes a smarter route. It does not necessarily replace silicon. It upgrades it. Manufacturers can keep the silicon wafer, much of the existing cell knowledge, familiar module formats, and established downstream equipment, then add a thin, high bandgap absorber on top. That is why compatibility with existing HJT lines is central to Tongwei's strategy. The less of the factory that needs to be thrown away, the easier the economics become. Higher efficiency can reduce costs outside the panel itself. Suppose a solar farm needs a certain amount of power. If every square foot of module produces more electricity, the project may need fewer panels for the same capacity. That can mean fewer racks, clamps, cables, foundations, electrical connections, and acres of land. Labor per installed watt can fall too. As module prices have dropped, these balance of system costs have become a larger share of total project cost. So efficiency is worth money even if the tandem panel itself costs more. The advantage becomes even clearer where area is expensive. A factory roof, warehouse, data center, parking canopy, or constrained utility site has a fixed surface. Once that surface is full, cheaper panels cannot create more space. A higher efficiency tandem module can produce more power from the same roof or parcel. That is one reason early tandem products may first make economic sense in premium, space-limited applications rather than the cheapest desert solar farm. But costs can move the other way too. The Perovskite stack adds deposition equipment, extra materials, process control, transparent conductors, and additional quality checks. Some tandem designs rely on indium-containing transparent conductive oxides, and silver use remains another industry concern. Tongwei has said it is working on low silver and silver-free metallization. Yield losses could also erase efficiency gains quickly if large area coating defects remain common. Then there is lead. Most of the highest performing perovskite solar cells use lead halide absorbers. The quantity is small, but lead is toxic. So damaged modules, disposal, recycling, and long-term leakage have to be managed seriously. Research has shown that encapsulation and lead capturing layers can reduce leakage dramatically, and recycling strategies are being developed. Still, commercial products will need robust containment and end-of-life systems, rather than treating the issue as somebody else's problem. None of this makes the 776-watt module less important. It tells us what the milestone actually is. Tongwei has not announced a finished mass-market panel that will immediately replace today's silicon modules. It has demonstrated a large industrial format tandem module, raised full-size cell efficiency beyond 32%, and pushed an automated pilot line to an average above 28%. Those are manufacturing milestones, and manufacturing is where perovskite tandem solar has historically had the most to prove. The next numbers to watch are not just another champion efficiency figure. Watch pilot line yield. Watch average efficiency. Watch module efficiency over full area. Watch degradation after extended outdoor exposure. Watch whether Tongwei follows its 5 megawatt line with the previously discussed 100 megawatt pilot stage. And eventually, watch cost per watt and warranty length. Those will tell us when the technology has crossed from impressive engineering into a bankable product. If tandem modules can hold their performance for decades and factories can coat enormous textured wafers at high yield, silicon solar will not disappear. It may simply gain a second junction and keep going. That is why this is potentially the biggest upgrade to mainstream silicon since the industry began moving from older PERC cells toward TOPCon, heterojunction, and back contact designs. Those technologies improve how silicon handles charge. Perovskite tandem changes how much of the sun the device can use in the first place. A 776-watt number makes a good headline, but the 5 megawatt pilot line may be the more consequential machine. It is where chemistry has to become manufacturing, where microscopic films have to survive industrial handling, and where record cells have to become repeatable products. If Tongwei and its competitors solve that transition, solar panels could move beyond the efficiency range that single-junction silicon can realistically reach without abandoning the silicon factories already spread around the world. So the question is not whether Perovskite-Silicon tandem cells can work. They clearly can. The real question is whether they can be made cheaply, uniformly, safely, and durably enough to compete with one of the most optimized products modern industry has ever produced. What do you think matters more for the next generation of solar? Pushing efficiency above 30%, or proving a 30-year service life at a competitive price? Let me know in the comments, and subscribe to Eastern Engine for more technology, machines, factories, and engineering coming out of China.